Hey everyone, welcome into the last video in this lecture series on the cross product. In this one we'd like to solve a problem here, an example in 2 dimensions. So let's suppose that we have 2-dimensional plane, so our xy plane, and let's suppose that we have a line, and I'll say that this line has formula in standard form here, so mx plus b, alright, and a point, say point P here, that's not on the line. All right, and if we need to know the coordinates of the point, then that's fine. We don't even really need to know the equation of the line yet for what I'm about to do. But what I would like to do is use the cross product now to determine the distance from the point to the line. So this is the question. So can we use the cross product to determine this distance d? So the answer is of course yes, but what we can do, let's suppose we have a couple points on this line. So let's say we have this point and this point. Let's call these Q and R. Then what we can do is we can make a couple of vectors here. So we can make the vector QR, and we can make the vector QP or PQ, however you want, but this vector. And then we can think about this, right? So let's suppose, again, D is our goal, right? We want to find the distance here. So the distance then, if we were to take the cross product of these two, then QR cross QP would be a vector that points straight out of the screen at us, right? So I'll try to draw it maybe like this, coming straight out of the screen at us, and it's perpendicular to the plane of the screen. So this is going to be our cross product. The way I've done it here is QR cross QP. It doesn't matter though. And remember the length of this vector, so the length of QR crossed with QP is equal to the area of the parallelogram, right? So it's equal to the area of the parallelogram that's determined by these two. So what's that parallelogram look like? Well, you just slide this vector over and you get this nice parallelogram right here. Use your imagination. All right, so that's one way that we can compute the area of the parallelogram. But remember, the area of a parallelogram is also given by, so if you just look at it this way, it's given by the base of that parallelogram. So it's given by the base times the height, and the height's exactly what we want, right? And so we know, again, further here, that the area is also equal to base times height, right? And so if we rearrange this, by the way, we know the base as well. The base of this is the vector QR, so it's the length of QR. So this is the length of QR. I didn't put my hats on my vectors. So it's the length of QR times the height, and the height is the d that we want, right? So if we set these all equal to each other, then we're going to get a nice formula, right? These have to be equal to each other. And we're going to get a nice formula for the distance d that we're looking for. So just setting these equal, we see QR cross with QP is equal to this d that we want times the length of QR. And so I'll back up here. What we end up with is that the distance from the point P to the line determined by QR, right, by the 2 points on the line QR, this is going to be given by the length of the cross product, QR cross QP, divided by the length of QR. All right, so we're going to use, by the way, we found a formula for this using a dot product in the previous set of lectures, in the dot product lecture series. So now we have a dot product method and a cross product method for finding the distance between a point and a line. Let's do an example. So let's suppose that we have a point, let's say 5, -1. And we have a line whose formula is y equals 6x minus 3. All right, and we want to find the distance between the point and the line. So we want to find the distance. All right, and I want to use this cross product method. So the first thing we know, we have the point P, right? We need 2 other points. We need points Q and R. It doesn't matter what those 2 points are. They just have to live on this line, right? They have to live on the line. So let's just take our Q to be the point where x is equal to 0, right? So let's set x equal to 0. So then what would y be? Y is going to be equal to 0 minus 3, so -3. And so our point Q can be 0, -3. And then our point R, let's just do the opposite, right? So if y is equal to 0, then what happens? Then we get 0 equals 6x minus 3. So what's x have to be? So x has to be a half, right? And so this point is 1/2, 0. All right, and so we can now use these 2 points to create our vectors, right? Or these 3 points, really. We have 3 points here, right? So we need vectors QP. QP is terminal minus initial. So this one's going to be 5 minus 0, and then -1 minus a -3. So 5, 2 for QP. And then we need QR. QR is going to be what? The vector, so 1/2, and then 3. Okay, so there we go. There's 2 things. In our formula, we need the length of QR. So we'll have to find the length of this one. And then we need to somehow take the cross product of these 2. So let's start with the one we know how to do. So the length of QR, this is just the sum of the squares square rooted, right? So this is 1/4 plus 9, all under a square root. So this is the square root of 37 halves. If you add this up, it's 36 plus 1, all divided by 4, take the square root. So there's the denominator of our distance. And then now we need to somehow think of how to take the cross product. But our cross product is a product that only works on vectors in 3-dimensional space, right? So if you have a 4-dimensional vector, you can't do it, right? You just can't do it. But with 3-dimensional vector, with 2-dimensional vectors, I should say, you can do it, because you can imagine that these are the XY coordinates of vectors that live, say, on the floor of the room that you're in. And if they're on the floor, then their z coordinate is just 0, right? So to take the cross product, we can just think of this as 5, 2, 0, and this one as 1/2, 3, 0. All right, and then we can take the cross product of these 2. Cross these. And remember, we just need the length of the cross product, but we have to compute the cross product first, right? So let's do it. So Q, by the way, the order is not going to matter for us because we only care about the length. So I'm going to do it this way. So I, J, K, I, J, right? I'm going to use my fancy method here. So this is 5, 2, 0, 5, 2, 1/2, 3, 0, 1/2, 3. And then get out the highlighter. And this times plus this, multiply those together, minus this, this, this. All right, so we've seen a couple of videos, hopefully, up to this point, and hopefully this method's okay. But this one's going to be 0i. There's a lot of zeros here. This is good news, right? Plus 0j plus 15k. And then minus, don't forget the minus, so this is going to be 0j plus 0i plus, this is just going to be 1k. 1/2 times 2. And when you combine this all together, you get 0i plus 0j plus, then you have 15 minus, this was a 1, right? I just wrote k, but minus 1. So this will leave us with 14k. And then, of course, the length of this vector. So this vector is 0, 0, 14. And so the length of QP cross with QR is 14. We've got the length of QR up here is this. We just take the ratio now, right? So the distance, D, is equal to, I'll write the formula again one more time. QP cross QR over the length of QR. So for this is 14 over root 37 halves, which is 28 over root 37. And we are happy to leave the square root on the bottom of this. If you want to rationalize it, you can, but this is a beautiful answer. So we'll leave it there.